Coming to DARPA is like grabbing the nose cone of a rocket and holding on for dear life.
DARPA's a place where if you don't invent the internet, you only get a B.
A DARPA program manager quite literally invents tomorrow.
Coming to work every day and being humbled by that.
DARPA is not one person or one place. It's a collection of people that are excited about moving technology forward.
Hello, and welcome to Voices from DARPA. I'm your host, Tom Shortridge. For decades, DARPA has made investments in quantum research, laying the foundation for next-generation capabilities such as positioning, navigation, and timing in GPS-denied environments, ultra-secure communications, and even quantum computing. Now, if you're like me and don't have an advanced degree in the field, your concept of quantum is probably heavily shaped by pop culture and science fiction, where quantum is essentially indistinguishable from magic and can do whatever the story wants it to.
Quantum anomaly.
Quantum research.
Quantum entanglement between the quantum states of
quantum technology. Quantum energy.
Quantum system.
Quantum healing particle. Quantum tunnel.
Do you guys just put the word quantum in front of everything?
Today, we're sitting down with Dr. Joe Altepeter, program manager since 2019 in DARPA's Defense Sciences Office. Joe is deeply interested in quantum and quantum technologies and runs several DARPA programs on the subject, which we'll get into a little bit later. But first, so we're all operating from the same baseline. What exactly is quantum?
This is a huge question. It's like, what's quantum? How do you have a definition that unifies all the quantum communications and the quantum sensing and the quantum entanglement and quantum teleportation? How does this all fit together? My normal answer to this kind of goes against the pack. I'm like, well, it's really the wrong question. There is no one quantum. People put that on everything. Like they just call everything quantum because it sounds sexy and it's going to make their project sound cooler. But at a basic level, quantum mechanics, like quantum physics, like what you get if you take a quantum course in your undergrad, it is the physics of what happens when the universe gets really small. It's the physics of how light works. And really, it's the physics of everything. It's our most basic level of understanding of how chemistry works, of how biology works. Really, almost any subject of science we have, if you dig down enough, you get to quantum.
Okay, that doesn't sound too ridiculously complex. What about, there's another term that comes up a lot when people are talking about quantum, entanglement.
Entanglement is the heart of quantum mechanics. If you put something in a quantum superposition, that object can really exist in multiple states at the same time. It can be strangely, weirdly correlated with other particles on the other side of the universe, such that if something happens to one, you learn information about the other one faster than the speed of light. All of that is true. It's exactly as weird as it sounds. And it's actually not a lot more complicated than that. It's just at that point, people are like, that's crazy, I'm out. I'm just gonna replace quantum with magic in my brain, and that's that. As soon as people hear quantum mechanics, they turn their brain off.
I'll admit I'm guilty of that.
It's just linear algebra. Like really, it's just adding and multiplying numbers. It is not hard. It's surprising. It's not hard. And most people get surprised, and then they decide that they just misunderstood it. And so they're going to need a professional to work on this. But that has led to a ton of hype in this field. Even more so recently as like venture capital gets involved, and now there's billions of dollars flying around and everybody wants a piece of that. And people who are outside of it assuming it's going to magically solve their problems, and people who are inside it maybe not pushing back as hard as they could because they would prefer to get that grant than explain why you really can't use entanglement to communicate faster than light.
So where do you see DARPA's role in this space?
What I've always loved about DARPA is interested in the truth. And they are willing to celebrate a negative result just as much, if not more, as a positive result. And so what I think DARPA should be doing in this space, and what I have tried to work to make them in this space over the past 4 years, is an honest broker. We should go in being totally fine if the answer is quantum mechanics. Yep, it's going to change the world. We think it's going to change the world in XYZ way, and this is how we're going to help make that happen, or get out of the way while industry does it. Or we're going to say, nope, really is hype. Quantum mechanics, super interesting, totally useless. And so From my perspective, the most powerful thing DARPA can do in this space is figure out where we are on the spectrum between totally useless and completely transformative. We have narrowed it down. It's somewhere in that zone, but it's going to take some work to get it narrowed a little more.
I feel like you're underplaying it a little bit. That seems like a lot of work.
I have always had a weakness for impossible problems. I get sucked in. Somebody told me in my first year of grad school, like, oh, you can't use entanglement to communicate faster than light. And I'm like, maybe you can't use entanglement to communicate faster than light. And like 3 weeks of my life devoted to that problem. Spoiler alert, you cannot use entanglement to communicate faster than light. But it was super fun 3 weeks trying to do that. So when I was an undergrad, I wanted to do everything. I came in with a list of like 15 possible majors, from like European history to computer science. And after my first couple of years, I had my first quantum mechanics class in my sophomore year. And I got a B, which was like, I was outraged. I was like, well, how is this possible? It was possible because I was, spending a little too much time in my European history class. It wasn't coming to lectures, and it's entirely my fault. And so my solution was, I am going to skip the next quantum mechanics course, and I'm going to go straight to graduate quantum mechanics, because I just got mad at the problem, and I'm like, I'm going to completely destroy this quantum mechanics, and I got to be in that for obvious reasons because I skipped a class. And I came out of my undergrad having taken every quantum mechanics course except for the one that I skipped, gotten a B in all of them, and gotten an A in everything else, and I'm like, this is what I'm going to do. And so I went to this like undergraduate research program. I went and worked at Los Alamos with a guy called Paul Kwiat, genius. Just by luck, got to be involved in making some of the very first real sources of entanglement that you can touch and play with and prove are as strange as all the paradoxes you read on the news really are. And it was great. And then after that, I was off to the races, and I'm like, I'm going to be a physicist. This is going to be fantastic.
So now, how did you end up at DARPA? Can you kind of walk me through that journey?
So I started off on the academic path, right? And I was, wandering around. I did my undergrad at WashU in St. Louis. I did a Fulbright scholarship in Australia. I eventually followed my advisor from my undergrad research, who got me online with that Fulbright path, to Illinois at Urbana-Champaign. And I went to a postdoc at Northwestern, and then they hired me as an assistant research professor. But along the way, I met my wife, who was a medical doctor, and I don't know if you know people who've done this before, but you go through the residency and fellowship, and the computer sends you someplace, right? And it sent us to Chicago, and that's how I ended up in Chicago. And then it sent us to Delaware.
Hi, I'm in Delaware.
And so I had a couple of choices, right? So Delaware, there's giant banks there. So I could be a quant for a big bank. I could commute from Chicago as a professor, or I could do the Joe Biden commute and Amtrak down to DARPA and help them try to figure out some science. And so I did the 3-hour train each way from Delaware, 14-hour days, while she was training in Delaware, and I have never looked back. It was amazing. So I was a CETA, I was a subject matter expert for DARPA, for IARPA, a huge variety of programs. One of my first programs was on lightning. I did ones on quantum biology. I did ones on quantum computing, which is what we'll talk about today. But at the time I had to make the call of what should I do with my life. It was really difficult. I'm like, I've always wanted to be an academic. I want to go the full professor route. I want to, make a difference. And man, as soon as I got into DARPA and IARPA and the ARPA world, I was hooked, because there is no impact that you can make like a DARPA impact. So I did that for almost 10 years. And then Valerie Browning promoted me to a PM almost exactly 4 years ago, and here we are.
And you're running a few programs dealing with quantum technologies, right? Can you walk me through those?
So right now I have 2 active programs, and it's been a long journey to get here. One, quantum benchmarking, is about a little over a year into its lifetime, and so we're starting to learn some things. The other, US2QC, Underexplored Systems for utility scale quantum computing, just started. So I think we're 5 months into that, maybe 6 months into that. So they really look at 2 halves of the same coin, but exactly what I was talking about, of let's just go in, an unbiased view, and try to figure out what is going on. So there's 2 sides to that question. If I think about the smartest physicists I know who are skeptical of this, they're skeptical for 2 reasons. One, you'll never be able to build a quantum computer. And even if you could, it's never going to be more useful for a real problem that you care about than your laptop. And my 2 programs handle those 2 things. So quantum benchmarking is Just imagine you had one. Magically, a genie gives you a gigantic, perfect, super fast quantum computer. What do you do with it, and why is that important? That is what quantum benchmarking is designed to answer. And specifically, because it's a DARPA program, we care about metrics. We don't care about emphatic statements someone defends. We care about, give me a quantitative yardstick that you can prove corresponds to positive impact on a problem we care about, and then show me why you think the quantum computer you're going to build, or that the genie gives you, is going to score high on that yardstick. This program is about making those yardsticks, which is a lot harder than it sounds. The other program, US2QC, is about okay, let's assume that it's going to be useful for something. Can you build one? Because these machines are insanely complicated. People use analogies like, it's like building a rocket ship to the moon. It's not that far off in the level of technical difficulty to get to the really big, really accurate versions of these machines that people are talking about. Maybe it'll revolutionize the pharmaceutical industry or other problems like that. And so it's saying, well, DARPA's not going to build one of these because, like I said, there's billions of dollars in this space. And DARPA's opening position is skepticism. Like, we walk into the room saying, we're pretty sure whatever you're doing is not going to work. But we want to listen. Like, I will bring a small army of scientists and we will listen to your argument and we will double check and we will do our own analysis. And if we're convinced, we will tell the rest of government that, and we will become a strong advocate for whatever we found. Let the chips fall where they may. That's what US2QC is all about. It's the software and the hardware sides of the problem.
So when you're talking about quantum computers, quantum computing, how is that different from what we're using today, our laptops, our cell phones?
Classical computing, I think everybody who's listening to a DARPA podcast is going to be comfortable with classical computing being based on bits. Every bit is a 0 or a 1. That's the basic unit, a yes or a no.
Here's a suggestion, computer. I assume you read binary, so why don't you 011, 1111, 011, 011?
A quantum computer also uses quantum bits, but instead of just a yes or a no, they can take on one of an infinite number of different flavors of maybe. This is the part that gets you got that look in your eye, like, oh, quantum is magic. Yes, it's going to sound like I'm trying to simplify a much more complicated topic that I should have a lot of Greek letters to explain. But it really is as simple as the bit can exist in multiple states at the same time and in different ways. I can have different balance of 0 and 1 and a different kind of character to how they're mixed together. And you can extend that to the rest of the computer. Really, if I have 1,000 bits, the computer can simultaneously exist in any number of combinations between those states. To be clear, when I say a quantum bit, everybody in the news is going to call these qubits, which is a super cute and clever name. Qubit equals quantum bit. They're exactly the same.
So when you're talking about a quantum computer, is it kind of standardized like a classical computer in that it has a motherboard, a processor, memory, storage, or is it something else entirely?
This is actually one of the things that makes evaluating these technologies so hard because they are completely different. Like, you imagine a quantum computer, you imagine some crazy science fiction technology. That's largely true. But what you may not imagine is it's like 8 different kinds of crazy science fiction computer. Some proposed quantum computers calculate using individual ions, like a single atom that has an electric charge trapped in some electric field, dancing next to 1,000 other ions and all talking to each other. That's what we call an ion-trapped quantum computer. There's some others where you trap neutral atoms that don't have a charge in some network of lasers, and they all kind of hang in space suspended on a network of light. There's others that use superconducting resonators, tiny little loops of wires cooled down to 10,000th of a degree Kelvin above absolute zero, like close to the coldest things we can make on Earth, to run your computer, and then these kind of superconducting resonators talk to each other through magnetic fields. Some people want to build these out of photons and make circuits of light on a computer that looks a lot like the motherboard that you're imagining, except it's light instead of electrons running through. And there's like 8 other different kinds, which means Then we think about trying to figure out if these work. We need experts in completely different technologies, which talk totally different languages. And the metrics for one are totally useless to describing another one and trying to figure out what apples to apples means, not just for today's 100 qubit systems, but for the 10 million qubit systems we're hopeful will really make a difference for problems we care about. Whew, that's a DARPA hard problem.
Have you seen anything surprising this far along in the program?
Oh yeah, huge surprises. The thing that's going to be antithetical to a really interesting podcast, though, is one of the reasons, so I'm going to start on the USDC side, on the hardware side. One of the things that's going to be antithetical to an interesting podcast, and one of the reasons that DARPA needs to be in this space is, at this point, these systems are big money. People doing this are protecting this as super proprietary Fort Knox kind of information. And this is one of the reasons it's really hard for the normal academic environment to evaluate how well these systems work. Because you don't want to publish your secret sauce if you really think it's going to be worth tens of billions of dollars in 10 years. And so you need an honest broker where we can say, look, federal law says I cannot tell anyone anything you tell me about your proprietary technology. I will go to jail. That is a strong statement that you can't get from just getting any old quantum mechanics evaluator off the street. That's part of the reason that DARPA has a unique position in the space, but it also is one of the reasons I need to say things like, it's super interesting and super exciting what we're seeing for reasons I totally cannot tell you. I will be able to tell you if and when we're able to promote anybody into the next phase, which those announcements could happen as soon as in the fall. But the reasons why I'm excited about these technologies, I can talk about at a very low level. One of the performers we're working with is a company called PsiQuantum. They want to build their computer out of light. It is super exciting to build computers out of light because light is mostly immune to electromagnetic waves. Like it's that kind of the noise from cell phones and everything else that jumbles everything. Photons aren't jumbled by that in the same way, but they also don't really talk to anything in the same way, so they're hard to control. And so one of the questions we want to ask is, can you really build a scalable computer out of things that are so isolated they don't even talk to each other? What's your plan there? One of the other companies we're working with is a neutral atom-based company called Atom Computing. They have a really strong case that by building computers out of neutral atoms, you'll have options for how to control them and how to keep them stable that won't be possible in any other kind of technologies. Finally, Microsoft is investigating what's called a topologically protected state. Topologically protected states use the mathematics of topology to start off in a less error-prone aspect than other kinds of computers in the hopes that if you can build these things, which is super, super, super hard to build, you'll have a jump start to get the rest of the way there. I can tell you that for the program as a whole, I'm super excited and watch this space, and maybe someone's going to go into phase 1 come the fall.
And in those examples you just gave, you're talking US2QC, right? What about quantum benchmarking?
Quantum benchmarking, I think I can talk a lot more about what we're investigating. We designed this program to go broad at the beginning because people really do recommend quantum computers to be the solution to everything and the kitchen sink. Like every kind of problem that could plausibly have a computational bottleneck and a bunch that don't, people are pitching quantum computers to solve. So we said, let's go broad and have our performers talk to lots of subject matter experts in tons and tons of fields. Let's look at over 200 individual specific problems where there is a computational bottleneck. Let's try to define that clearly. Let's try to figure out what you would really need to make a difference. Let's think about, is there an argument for quantum computers being in this space? And then let's narrow that down. And we're on track by the end of this summer, 18 months into the program, to select the half dozen or so problems that we then want to use the next phase, the last phase of the program, to go deep. So I can say that has worked really well. We have some fantastic performers who have made a great argument that, yeah, we really do think that there's 5 to 10 problems where it's plausible you could get a quantum computer to have a really big impact, not a small impact, at the size of 10,000 logical qubit or smaller system, which I was absolutely not sure we would get there. I definitely thought there was a chance at this point we would say, nope, we looked pretty hard, but I see a lot of smoke and no fire. There's nothing more for DARPA to do here. But I think we've got a pretty strong case, And so if this program goes into phase 2, I think we'll have a half a dozen real problems to take a close look at over the next 18 months.
I'm going to switch gears a little bit here. I'm always fascinated by how sci-fi might influence or inspire the work that DARPA engages in. What's your relationship with sci-fi like? Are you watching anything or reading anything now?
It will not surprise you that I haven't had a lot of time to read in the past 4 years, because this is like, you just leave it all on the field as a DARPA PM. But I love science fiction. Like, I think it's fantastic, especially the hard science fiction novels like Peter Hamilton, where they make some crazy assumption and then they take it to its logical conclusion. So you try to be as faithful as possible to science, except for a small set of things that you change and you just see what the consequences are. Actually, that is a lot like what we do at DARPA, is figure out if we break one assumption, what are the consequences, and then how do we pull that off in real life.
And you've been at DARPA for a while now, as both a CETA and a program manager. Any words of wisdom for somebody who might be considering joining the agency?
Oh, you should jump at the chance. Absolutely. Like, the opportunities are going to be few and far between, and you're going to need a lot of hard work and a lot of luck, but you will never work someplace where you have as big of an impact as DARPA. I think out of the 100 people I know well enough who are former program managers to know their answer to this question, I think 0 of them would say that this was not the best job they ever had. You're exhausted. Like, it's a marathon. Like, it takes everything there is out of you, and I've never worked this hard at anything in my whole life. A lot of times people say, kind of as a throwaway comment, like, oh, I'm trying to change the world. Like, at DARPA, you really have a chance to have a great idea, and then 9 months later, 6 universities, companies, government labs all have a dozen brilliant people all working with tens of millions of dollar budgets to try to make that a reality and try to change the world according to some idea that you champion. It's intoxicating. It's the best feeling ever. You should jump at the chance.
That's all for this episode of Voices from DARPA. Thanks for listening. And thanks to Dr. Joe Altepeter for joining us. You can learn more about his programs in the show notes or at darpa.mil.